I just wanted to point out that the project actually received a significant amount of money from the Inflation Reduction Act, which buffers the project now until CD3 from the vagaries of, for example, the continuing resolution process, et cetera. So the project is very, very well positioned to track this path to a CD3 in 2025. Again, just to mention that one of the recommendations that came out of the hot and cold QCD is not only the construction of the EIC, but support for the EPIC detector within the EIC. And so let me just finish up here, hopefully not too far out of time. I hope I've shown you that the EIC is a fundamentally new QCD laboratory that's designed to elucidate a wide range of the properties of quantum chromodynamics and how it matters in terms of the kind of matter that we interact with every day. And I hope I've maybe given you a glimpse of how that interacts a bit with the kinds of physics that we've studied at RHIC. I think the EIC science goals in many ways are a natural extension of now applying precision to the kinds of studies that we've done in relativistic heavy ions. And I hope I've shown you that the EPIC detector is rising to that challenge, to that scientific challenge, to produce a detector which can address the full EIC science program. And with that, thank you very much.
Thank you, John. That was wonderful exposition of the EIC science, and particularly the connections you try to make to the heavy ion physics. So I think that was new. I think I will definitely have to think a little bit more about this. So I think it was wonderful that you tried this, and I think it works wonderfully. Making so let's go to the audience. Please raise your hands, and I will then call on you to talk. And if someone I miss, apologize in advance, but just speak up, or maybe Nu also can see who else has raised hands. So Nu, go ahead. You're the first one.
Yeah, thank you, John. I have been watching. As no, I haven't seen any hands, so that's all right. I think, John, very nice talk. Thank you very much. I learned a lot. I have one technical question. I think on slide 26, you mentioned the magnet strength 1.7 Tesla. Is this a new solenoid going to construct it, or it's a used one from current one? I thought it was 1.3 or 1.5 Tesla. Is that right? So.
Yeah, that's right. So this is a brand new solenoid. This will be a new solenoid. So the original plan in the ECHE proposal was to reuse the solenoid from the Babar solenoid from the S-Phoenix experiment.
Right.
And we started, and when we started looking at that, we encountered a number of challenges, right, in terms of using it. It really puts, because it has a lower field, it puts really high demands on the tracking. And when we started looking at the magnetic field design, so in Phoenix, the plug doors are in fairly close. The plug doors are, the flux return is actually pulled out a little bit more, and it's asymmetric in EPIC. What we found was that would result in an even lower magnetic field than 1.4 Tesla, which would put even more severe demands on the tracking. One possibility would be to run the Babar solenoid at a higher current, but that is an R&D project, and that would require opening the cryostat to examine the coils and magnet before we even tried that. And it was felt that that's too much of a risk. So by going to a new magnet and a magnet which runs at a slightly higher field, we're still able to maintain a magnet which is relatively thin. And that was one of the key benefits of the Babar solenoid. It was only 0.3 interaction lengths, right? We can design a magnet which is just a little bit more, about 0.35 interaction lengths, get a 1.7 Tesla field, which relaxes the requirements on the tracking and allows us to work within existing MAPS technology. And so that was really a win. And we can design the magnet to work well with the asymmetric flux return.
Then what will happen for this Barbar magnet? Will that be used for second detector, or it will be abolished after S-Phoenix?
Well, I think the answer is that the Babar magnet would be available for other uses. I don't want to speak for the second detector. I'm sure that those people have some very clever ideas as to what they want to do. If that works with their plans, it would in principle be available.
I see. Okay, thank you.
Well, if I may just add to that discussion, I think currently the new magnet is being designed is exactly the same size and characteristic. The physical size is identical to the Babar.
That's right.
And the way to reduce the contingency, the risk contingency, in spite of being a new magnet, is to say that the fallback would be the one that we will use, that HA initially proposed. So that's you should look at it as a backup for a new magnet, and that effectively reduces the risks total overall.
Well, we don't say that anymore, Abe.
Well,
and the reason behind that is once you say that your baseline field is 1.7 Tesla and you design your tracker to that, right, you're set. What is true about the new magnet design is it's actually being designed for 2 Tesla, but the current density is low enough at 1.7 Tesla that the magnet cannot quench. So it's an extremely conservative design, right? And we believe that we will absolutely be able to obtain 1.7 Tesla, and we can run at 1.7 Tesla with the magnet being impossible to quench. And so you're right, there's always risk with a new solenoid development, but this solenoid is being developed to such a conservative set of parameters that is really the way that we're mitigating that risk.
All right.
Yeah.
Let's look at any other hand. Anu, did you have more questions or comments?
I'm a little bit out of date. So I thought the HR detector was selected as a base detector. Partly is because using this existing bar detector to save the cost. Now I think the EPIC will change at least on this selection, change the directions. And
oh, I'm sorry, go ahead.
Just if I look forward, that means the second detector may not or likely not use the Babar detector. That means we're going to have two new magnets. And my main question, actually, I'm not worried about the cost. I think first physics should always go first. Cost is important, but we should not limit by the cost, but limit the physics by the cost. Now the question is, what will happen to second detector, and what complementary physics program could bring to the EIC overall program? Maybe it's a question more for both John and Abe. This is new. I'm very interested.
I think that's a very good. Question. Just to comment on costs. The cost savings from using the Babar magnet itself was not that large. The cost savings to the tune of about $13 million comes from reusing the outer hadronic calorimeter, which is why the new magnet is designed to fit within the same envelope. With regards to the second detector, the second detector has a number of challenges, and so there is to set the stage. There is a EIC users group working group now formed around the second detector, and they've been having meetings and workshops to define the physics goals and the reach of the second detector. The second detector has a number of hurdles that it has to cross. The first of which is that it should have some overlap with the science program of the first detector, because we want some complementarity between the two. We know that groundbreaking discoveries measured only by one detector and one collaboration are complicated. And it would be nice to have confirmation for those kinds of discoveries that we expect at the EIC. But there needs to be complementarity also implies difference, and there has to be something that the second detector brings new to the physics program and expands the physics program for the EIC. And again, I'm just talking for myself here. And so that is a complicated thing to do. And there are a number of people who are working very hard to sort that out. I think that's why it's important that the second detector be given time to actually evolve the science arguments and the argument for a second detector. In no small part because one of the problems at the EIC is that unlike RHIC, your being limited. And so if you collide at 2 interaction points, each experiment gets half the luminosity. So there is a trade-off if you build a second experiment, and that does sort of obligate it, I think, to come to the table with something that broadens the physics reach and allows us to expand in new directions. But Abe, you should.
No, I think I agree with most of the things they've said. I think it's very clear. The only thing I would add is that I think the facility providing a geometrical location for such a collider is something that it's very hard to give up that possibility. So I think we really need to push ourselves to think about, as John said, physics complementarity, and also possibly technology complementarity. And both of those will require some time with the first detector, right? Operational, that will allow us to understand what are the limitations of this wonderful detector we are building. I think we are trying very hard to make it as comprehensive as possible and as best as we can. And then we are challenging ourselves to say, okay, I want to do something complementary to a comprehensive detector. How do we do that? So I think the history, I would go back and say I think the same arguments were made for H1 and Zeus detector. They said, we will measure all the things that we want to measure at that time that we knew. And then they realized that they were weak in the very forward region. Now we have focused on that in the low X and the very forward detector. So I think that when the first detector comes in, there will be some surprises. And we could then launch a real campaign for the second detector based on what we are learning. And sometimes it doesn't mean that we have to wait for 15 years. It could be that we will find something in QCD in the next few years, which we will immediately realize, aha, we probably won't be able to get there. LHC will tell us something, RHIC will tell us something, CDM will tell us something that will come up. And I think we should be alert to all of that and make the science with the overlap, but complementary. So I agree with John. I think it is going to take a little extra time. And it is a good thing because the speed at which the project is pushing us to go forward is breathtaking. So I think it's not bad to wait for some time, and depending upon how we can make the idea crisp, and then we have to make the justification for that cost. So it will take some time.
I don't see any other hand. We have.
I see Yushin. Go ahead, Yushin.
Yeah. Hi, John. Very nice talk.
Hi.
Thank you. I have 2 questions, if I may. One is related to near threshold production to access the information on proton mass, and according to the formalism on your slide, so the valuable data will be at t equals to 0. So as we know, we never reach t equals to 0. So this is similar like the proton charge radius study. So the winner is always who can reach the lowest Q square in that case. And in this case, the winner will be the one who can reach the lowest T. So in that case, you really need to lower down the central mass energy for the collision with and this. If this is the case, the production cross-section drops significantly. So you need to increase the luminosity at this point, right? So a collider with a lower central mass energy but with the higher luminosity is required to do this kind of study. So I don't know what is the consideration based on the current central mass energy as well as luminosity design at the EIC for this kind of physics.
Very good question. So first of all, it's right. It's the extrapolation to t equals 0, right? That ultimately gets you access to at least in this formalism, right? And again, a number of people are looking at this in many different ways. It's the extrapolation to t equals 0 that sort of gets you access to that form factor. But in terms of the model dependence, right? You need to be able to constrain the measurements over a wide range in Q squared, as well as a wide range in terms of the energy of the virtual photon-proton system, right? Because it's that multidimensionality that allows you to test any model dependence that goes into that formula that I had on the other slide. So it's not just that you need to measure only at a point in phase space. You do need to measure it, as I understand from the experts I've talked to, you need to measure it in a multidimensional fashion to eliminate model dependencies. Now, in terms of measuring this at different center of mass energies, if you take a look at, if we go back to this here, you do have the availability of different center of mass energies, but as you go to very low in center of mass energies, your luminosity does begin to drop, right? And so this is probably more of a luminosity driven process, which is why these projections, I think, are shown for one of the sort of middling energies for 10 on 100, sort of a compromise between these. Nevertheless, with 100 inverse femtobarns, which is about a year of running, you can see that yields a pretty good measurement with reasonable systematic and statistical errors in, with a multidimensional character to it. If you were to find something here, you can imagine even a multi-year campaign to optimize both the detector and the machine to map this out in even more detail. Does that help address what you were? Yep.
Yep.
Yeah, very good question.
They could use the upsilon here at a high energy.
You could also use the upsilon here at higher energy, but I think you would absolutely do that, right? Because you want to observe this in multiple examples. But I think at higher energy, I haven't looked at what the cross section would look like compared to JSI. You're probably never going to get the statistical precision that you get, or as multidimensional an approach with the upsilon. But there are people talking about doing with the upsilon as well. Absolutely.
I think Yusheng is one of the people who's actually calculated this quite detailed. So I know that.
Yeah. You can also try to do it with other vector mesons, right? With lower vector mesons. I mean, people are talking about doing this with phi. Phi is hard because you need low momentum kaons. But, in principle, also possible.
Yeah, I just want to remind people, just like electromagnetic form factor study, in early days, people have a huge amount of high Q square data, but in the end, if you want to decide the precise proton charge radius, the valuable data will be in the low Q square region. So, okay. The second question is related to this crab crossing. So for spin physics, the most important thing is the spin orientation or the spin direction of the proton with respect to the virtual photon at the collision point, right? And because you need to extract the various TMD effects and the GPD effects through azimuthal angular dependence. So this angle, the spin orientation angle, is quite important at the interaction point. So for the crab crossing design, right before the collision, you rotate the beam bucket in terms of momentum. And in that case, afterwards, you have no monitoring on the spin direction of the beam bucket. So I don't know how, in this case, how can we guarantee the spin direction of this beam bucket during the collision? Because if you want to determine azimuthal angle dependent modulation, this is quite important.
Oh, that's a very good question, right? How do I know that this, and how do I know that something doesn't go wrong and destroy my spin polarization?
Correct.
So I'm not sure I have the entire answer to that question. On the electron going side, we do have polarimetry for monitoring the electron polarization. We do not have local polarimetry on the hadron going side, although in the past we've used, for example, the ZDCs at RHIC to monitor the local polarimetry. I have not thought, I would assume something similar can be done here, but that's a good question. I have not thought that through.
So the existence of spin we can maintain, we can confirm because the same beam goes around. So I think that's the same thing. But what he's asking is the local polarimeter at the spot of collision. And I think I think we need to figure out, similar to the ZDCs, but also BBCs, what we had seen as StarX looked at finally, and now they calibrated exactly without the ZDCs, even with high luminosity and high multiplicity events. Our problem is going to be that it is going to be low multiplicity, even event by event. So I think we need to figure out, but it is something, some relation, some interaction like what we discovered and what we honed in at RHIC will have to be done, either by zeros very forward or charged pions very forward. Look for those asymmetries and figure out, calibrate transverse first and then go to longitudinal, as we did in the RHIC.
Exactly.
And then you have to argue that the remnant, you have to put a limit on the uncertainty we have on the longitudinalness of the proton at that point. I think that's the same thing we did at RHIC. But yeah, I think it's a very good experimental question we need to solve when we study on.
Yeah, polarization is one thing, and the spin direction is another thing we need to figure out at the interaction point.
Yeah.
Right. Yeah, that would be the idea of studying transverse first before we go longitude.
Yeah.
Yeah. Thank you, John.
Yeah, you're welcome. Thanks for the question. That was great.
Anyone else? Oh, Lou, your hand is up. Is that old or new?
If there's no others, could I ask another question? So
go ahead.
We can go back to slide 16, I believe. I remember about a year ago or two, there are quite a few discussions about how to connect proton mass measurement, so vector meson production and proton mass. Lots of discussions. I also remember they could not find a QCD connection to this. So I did not follow things. What is the status now? Maybe Bowen is also online, or Abbe and John, you may know, because I heard the discussion say this is no connection. In fact, meson production in terms of proton mass. So,
well, well, it's my understanding, right, that you need to select a particular process, right, and in order to be sensitive, and this heavy quark production at threshold, right, I think has been a very exciting process because it has the sensitivity to the trace anomaly contribution that you want, right? So again, it's a question.
There are a few QCD guys that got serious and try to dig in, and they couldn't. At that time, they could not find the connection rigorously, especially the diagram you show here, the Feynman diagram.
I think there is a certain degree of model dependence. So let's go back here, right? Everything I've shown here is based off of a particular decomposition, right? In this case, it's a decomposition from Shandong Xi, right? And that is not a unique decomposition of this Hamiltonian, right? It can be defined, it can be decomposed in other ways. And so I think that and I'm happy to hear people tell me I'm wrong. But it's my understanding that this is where the concern really lies, right? And where a lot of the model dependence really lies is the very beginning of how you do this kind of calculation. How do you do a decomposition of the components that contribute to the hadron mass in order to be able to write the form factor in the first place? This is not unique, right? And so that implies that there's a model dependence in how you do this.
I think yeah, sorry. Go ahead.
Oh, no, go ahead.
No, I think what Lou is referring correctly to the trace anomaly contribution that connects to the observable, the J psi and upsilon. And there was a major assumption made, or model dependency made by Karzev in 1996, and that paper was questioned often. And that was the main focus of the mass anomaly or mass question, whether it can be really connected. I understand that the model dependency still exists, but people at least feel that that's the only first path towards measurement of this kind. So it is the first step. It is model dependent, correct? However, I believe that I was at the workshop in ECT Star where they agreed that there was no other way to get there. So this was the first reasonable model that will come across and will be measuring it in the next 10 years. Note that J psi in this case will be measured very precisely in our solid experiment at Jefferson lab.
That's right. Yeah.
And then upsilon will come up at the EIC with a much lesser model dependency in terms of because of the higher mass.
That's right.
So the theoretical calculations become much more easier when you go to higher masses. And that's why people think that EIC will be important to do that with the J psi, with the upsilon will coming in. So that was, I think, what you were referring to. Is that correct? That was the one bigger one that people still have doubts about, but see no other way to get there.
They use this gravitational form factor. Correct. Is that gravitational mass form factor? And
yeah, and I think Yu Xiang's question in the beginning was, I think, related to that. I was going to say that if the Chinese EIC comes along at a lower center of mass, it would be a very good one to measure that. I think we have discussed that with that earlier. So, but it is true. But the model
I'm not worried about a low T in terms of experimental measurement, because I'm worried more about the first principle. Can we apply this diagram here to extract the information we are looking for? So.
But that's why I think the multidimensionality is so important. GluX has been able to put a data point on the plot, right? And that's probably about all that they'll be able to do.
Yes,
you have to measure this. You have to measure this over a wide range of kinematic phase space, right, to be able to address the model dependencies.
The GluX's approach is in question.
That's I agree. And to be honest, that's fine, right? That's great. That's how we do science, right? And it's all part of that feedback between theoretical calculations, which then require some experimental measurements to reformulate the calculations to drive new measurements. And so that's I think what we're looking for.
Yeah. Yeah. Thank you very much, John.
Mm-hmm.
Okay. Do I see any more hands? I do not yet. Don't think I've seen many more hands. If I'm missing someone, please speak up. All right. Okay. Well, then that's the end of our discussion. Thank you, John, for a nice elucidation of the physics of the EIC looked at it from a different angle. I appreciated that very much. And Nushu, I'm impressed by this sequence and series that you're running for many semesters. So thank you for coming in and being there to help me when my internet stepped out. So thank you all. And that's it. John, are these slides available somewhere? Can you send at least me a link? I'd like to think about a few slides more.
I can certainly send you a link. I haven't looked. There's an Indico page. Can I post them there, or do the speakers post them there? Or?
I'll send to us. We will put on the Indico. Yes.
Yeah.
Okay.
But
Sounds good.
I would appreciate a link somewhere earlier. I might start thinking about certain things while I'm on tour, triple.
Yeah.
Okay,
Look, I
great.
appreciate the thoughts and discussion in this. I think there's real value in sort of evolving.
Right. The phase diagram that you showed and the connections you made there, I think those are very important, and I think I should think a lot more about this. So I think I'll be talking to you more as well as Nushu, because I know he's also involved in that phase diagram. So I think to get to the heavy ion physicists, that's really important. I think I really appreciated that very much. Thank you.
Good.
Very good. Thank you. Yeah.
Thanks, everyone.
Thank you.
Good night, good morning, good afternoon, wherever you are. Bye.
Thank you, everyone. This is the last talk for this semester. So thank you all for participating, and happy holidays. See you
Happy
next
holidays. Yes.
You.
Happy holidays.
Bye.
All right.
Happy holidays.
See you all. Bye bye.
OK，会超我们结束了。
对，要不我们什么时候再开一个会讨论下一个 series 的问题？
影仪不是发了，你先 stop 这个 recording。
对，好的。
那个。